About the properties of waves. Waves are kind of interesting in a lot of ways. A wave is a way to transfer energy from one place to another without a net transfer of mass. Now, a couple quick definitions on it. Pulse is a single disturbance, one loop of a cycle. We'll talk about what a cycle means. A periodic wave is a continuous repeated disturbance. And sinusoidal waves are waves whose source vibrates with simple harmonic motion, the part that we've been talking about. Medium is the matter that the wave actually transfers through. Sorry, it's a few words there. And here you can see an example of a wave. Mechanical waves require some sort of physical medium to transfer through. For example, sound, disturbance in a slinky, water waves, you name it. And so some examples of physical media are water, air, a string, a slinky, a cable, you name it, are all examples of physical media. You can see here a drop in a pond. The water is the medium, and you can see the waves here moving. Those are the disturbances in that medium. Again, the wave is transferring energy from one point to another without the net transfer of water in this case. So electromagnetic waves, which are the ones that we're pretty familiar with, are interesting is that they do not require a physical medium. Electromagnetic waves can actually transfer through a vacuum. So outer space, for example. They're composed of oscillating electric and magnetic fields, and they don't need something for it to be in. Examples include X-rays, visible light, radio waves, in fact, the entire electromagnetic spectrum, which light is just a very small part of. We start out here with low-frequency radio waves, TV waves, microwaves, then we get into infrared, then visible light, then ultraviolet, X-rays, and gamma rays. These are all just oscillations in the electromagnetic field, just different frequencies or different wavelengths, depending on how you want to think about it. But again, all of these can transfer through a vacuum. They can also transfer through mediums like air and water and some optical media. One quick note here, this C here is the character that we use for the speed of light. Light moves at an incredibly rapid rate. In fact, for a long time, they thought it was infinitely fast. But it does have a speed. Took some experiments, but they actually measured it. So the speed of light, in a vacuum, is about 3 times 10 to the 8th meters per second. Ignore the S here. That's almost about the distance to the moon. So if you took a laser and bounced it off one of the mirrors that the astronauts left on the moon, it would take about a second to get to the moon and a second back. Even moving at the speed of light, the moon is still a fairly large distance away from us. Light from the sun takes 7 minutes to reach us. Light from Alpha Proxima, one of the closest stars, it takes 7 years. It's 7 light years away. So even at the speed of light, our universe is fairly large. So here's what I was talking about. If you've ever been stuck out in the surf, you'll notice that the surf actually doesn't take you to shore unless you're right near the shore where the water's breaking. Instead, if you're in the wave, you go up and down with it, but in reality, you actually go in a small circular path like this. And that's actually what's happening inside of the water. And here you can actually see the movement of water, not only at the surface, but down below. You get a transfer of energy without a net transfer of mass. Except at the shore, what happens at the shore is this bottom part catches on the bottom, and so then you just have the movement over the top as the bottom of the wave gets stuck on the ground, and yeah, then the water does actually break. But you get this one. Each little oscillation transfers energy to its neighbor, which then transfers energy further down. There are 2 major types of waves. Longitudinal and transverse, and we'll talk a little bit about each one of these. A longitudinal wave is where you send compressions and rarefactions along, in this case this is a slinky or a long spring, as an example. You've got compressions here and rarefactions, that's where it's stretched out, and these are moving along the spring this way. You can see a nice example of it down here at the bottom. This is a bunch of small simulated masses and springs, and you suddenly move one, and that compression moves down the line of springs. You can also have transverse waves, where you shake it up and down, And so here you can see a series of crests moving along here, and a series of troughs moving along here as well. It's moving this way again, but now the oscillations are actually vertical. You're moving your hand up and down as opposed to left and right over here. In the transverse waves, oscillations are transverse. That basically means perpendicular to the direction of motion. In other words, you're shaking your hand up this way and this way. In a longitudinal compression wave, you're moving your hand back and forth. It doesn't have to be a hand. It could be any kind of oscillation that might actually cause these kind of motions. So let's talk a little bit about it. In the introduction, we introduced the idea of a pulse or continuous wave. You can have a pulse or continuous wave either as a transverse wave, like I have shown down below here, or even as a longitudinal wave. In a longitudinal wave, you would just send one compression down. This would be a pulse wave down here, as you can see, unless you did it repeatedly and continuously at a regular rate. I just want to show you this one real quick. I always get a little kick out of this one. This one, if the videos work, I'm having a tough time here. You can actually see, let's see if I can click on this one. There we go. Here is a couple, or some physics students actually demonstrating the two types of waves. Down below there, you can see a longitudinal wave, the series of compressions and rarefactions moving along. And at the top, you can see a transverse wave. I always get this. It always looks so much fun. Every year I try to get some students to actually reproduce this, and every year it usually is an epic fail. It looks so easy. Trust me, it's not. So a little bit of details, and most of you may know this already, either from math class or some other point. The major parts of this, though, the top parts here are called crests. The bottom parts here are called troughs. There's a bunch of troughs here and a bunch of crests. The distance between the equilibrium point would be the point where there would be no wave at all along this line right here. So you can measure the amplitude of a wave, that's how tall it is, either by going from the equilibrium to a crest or equilibrium down to a trough. Those are both represented by amplitude, usually represented by a capital letter A. Wavelength is a distance between two crests or two troughs, or even 2 points of equilibrium. It's the idea that it's a point where the wave starts repeating. Wavelength, I'll just mention real quick, is represented by the Greek letter lambda. Lambda looks like that. So it's a little bit strange. You're like, ooh, strange new letter. Yeah, this is lowercase lambda. But you should be able to sort of recognize all those sort of pieces in a transverse wave. You also have it in terms of longitudinal waves, but it's a little bit trickier. Compressions are these regions here where things are pushed together. And yeah, here's a couple of compressions. I won't draw all of them this time. And rarefactions are the areas where it's stretched apart, here and here. Wavelength, either between middle of a rarefaction and middle of a rarefaction, again represented by lambda. Or you can go between a compression and a compression. Or, yeah, just about anywhere where you get a complete repeat. Amplitude's a little bit hard to show on this one. It's how much it is compressed and how much it's rarefacted. That's a little bit hard to show on these kind of waves. But it does exist. So let's take a look at a couple of transverse and longitudinal wave examples. In this case, I want to identify what type of wave it is. So water waves, what do you think? If you want to pause the video, you can even think about it. Is it a transverse or a longitudinal wave? If you haven't already guessed, yeah, they're transverse waves. I'll put a little T afterwards for that. How about light waves? What do you think? Are they transverse or longitudinal? Pause if you would like. Answer is, yep, they're transverse as well, just like water waves. What about sound waves? This one always tricks people up. Pause if you'd like. Answer is, they're longitudinal. You're like, wait, no, I've seen that, on oscilloscopes and things where you've got the little waves as people are talking to microphones. Yeah, it's a visual representation where the crests represent the compressions and the troughs represent the rare fractions. But for example, when you clap, that's actually generating a compression wave that moves out in all directions, and that's actually what you hear when that runs into your eardrum. How about radio waves? Pause if you'd like. They're transverse as well. As we mentioned before, the entire electromagnetic spectrum is a transverse wave. How about earthquake waves? Pause if you'd like. This one's tricky. It turns out earthquake waves are both transverse and longitudinal. There are certain waves that shake the ground back and forth. Those are the longitudinal, and there are transverse waves that moves the ground up and down. So kind of a trick question. You may have heard of PNS waves. Those are the two types of waves, both the transverse and longitudinal, and they travel at different speeds. Waves transfer energy, we mentioned that before, without actually moving things physically from one point to another. It turns out the rate of energy transfer is proportional to the square of the amplitude. If you want an exact formula, it turns out the energy is 1/2 times the spring constant times amplitude. Remember, you can represent that with a capital A squared. When amplitude's doubled, the energy increases as a factor of 4. If you triple the amplitude, the energy increases by a factor of 9. This is why surfing during large storms is so dangerous. You're like, oh, the waves are only, 4 times larger than normal. Well, the energy of those waves would be 16 times larger. And so when they slam down on you, it's a whole different aspect. So be careful of that. Wave speed. Wave speed is determined completely by the characteristics of the medium. For example, sound travels at one rate in the air in this classroom. It travels at a different rate when you're up in the mountains. Why? The air is less dense there. It travels much faster underwater, about 5 to 6 times faster. It travels even faster in like metal. Sound will go through metal almost, the velocity is ridiculously large. For an unchanging medium, though, the wave speed would be a constant. So, for example, going from air into the classroom to air in the hallway should be the same. You can actually calculate the velocity by multiplying the speed of a wave by multiplying the wavelength by the frequency. Again, remember, F here is frequency. Lambda is used for wavelength. And if you're curious, how do you pronounce lambda? It's sort of written this way. It's a Greek letter again. But it is used to represent wavelength. And the velocity is just in meters per second. Water waves move at whole kinds of different speeds, depending on their size and the depth of the water. So water waves are a little bit harder to work with, but for other waves, we can actually talk about, I won't write out, this is frequency, and V is velocity. For the electromagnetic spectrum, all of those move at the speed of light, 3 times 10 to the 8th meters per second. We've already talked about that. And for sound waves, it's about 340 meters per second. But the speed of sound depends on temperature, pressure, humidity, you name it. What happens if you go faster than the speed of sound? Oftentimes the speed of sound is called Mach 1. You'll actually produce a sonic boom. In this case, you can actually see the sonic boom being produced behind this fighter jet as it goes faster than the speed of sound. It actually has also a little jet cone here. As it exceeded Mach 1, or the speed of sound in air at that particular location. So here's some quick practice problems. I'd like you to try this. Again, pause the video if you would like. I'll show you the solution in a second. Microwaves travel at the speed of light. I should say, what is the frequency? When the frequency of the microwaves is 9 times 10 to the 9th hertz, what's their wavelength? Pause the video now if you'd like. How do we solve this one? We're just going to plug into the numbers. Microwaves are electromagnetic waves, and we're told the velocity. So their velocity over here is the speed of light. And we're told that the frequency is 9 times 10 to the 9th. So we'll plug that in here. Solving for the wavelength, we get that they're about 3.3 centimeters in size. So reasonably sized waves. You just can't see them, but they're there. Here's practice 2. A piano key is struck and the note F vibrates with a frequency of 350 hertz. Assuming the speed of sound in air in that particular location is 343 meters per second, find the wavelength of the sound waves produced by the string. Again, pause if you would like. Answer for this one, going through a very similar process, plugging in the velocity, which in this case is 343. They gave it to us here. And the frequency, which in this case is this 350, you can very quickly calculate the wavelength, which in this case will be about 1 meter long. Wave interference, or wave interactions. You can have basically two types. So let's say you have two waves moving in the same medium in opposite directions, wave A and wave B. What happens when they run into each other? They don't bounce off each other, but they'll simply add as they're passing through each other. So if each one of these has an amplitude of A, what's the amplitude? I guess I should draw it on both of these. What's the amplitude of the wave as they pass through each other? The answer is this one has an amplitude of 2A, twice the amplitude. And then afterwards they move through each other. So B continues in the same direction, A travels in the same direction. This type of interference where they add together and produce an amplitude that's even larger is called constructive interference. So yeah, just quick little notes about this one. Matter can't occupy the same space at the same time, but energy definitely can. Waves do pass through each other, and they're completely unaffected by that passage. But the medium will be displaced equal to the vector sum of what the waves would do individually. So you've got the two amplitude vectors this way. When they add together, when they're right on top of each other, we get a new vector that's twice as large. Here's some computer animations real quick on this one, just so you can sort of visualize some waves meeting each other. Here's two sine waves, and they don't bounce off. They really do pass through each other. So here they are right before they go through each other, and then here they are as they pass through each other, adding them at each point. There they are on top of each other. Continuing on, they went through each other. But you can also have, so here it is, a fast one again. Same thing. But you can also do interesting ones. What happens if you send a trough there? And if you didn't see it, for a brief moment it canceled out. Here's a square wave and a sinusoidal wave passing through each other. Here is another one again, this time a square trough. And you simply add them at each point, but you can definitely see them passing through each other. Sine and a triangular wave passing through each other. And this triangular trough and a sine crest. Yeah, all of these work. So constructive interference, we've already talked about it. If you've got two waves where the crests line up with each other and the troughs line up with each other, another way of saying that is that they're in phase, you end up producing a new wave that's twice as big, twice the amplitude. Here it is with a transverse wave. Here's what it would look like with longitudinal waves. Here, these are air molecules, and here we've got compressions. And these compressions line up with the compressions from another source. What happens? We get compressions then that are twice the amplitude, air molecules that are twice compressed. Same thing's true with the rarefaction areas. Those line up as well, and so we get a rarefaction that has even less molecules than before. Here's one case. It also happens in real life. Rogue waves are where waves from two different sources briefly meet. This is a U.S. Navy ship, and this is one of those rare recordings where it happened. Here they just hit a crest, and now they're about to hit a trough. And the bridge deck here is 3 stories up, and it just went underwater. Luckily, Navy ships are designed to withstand this. If this happened to a large passenger ship, it may not be as so good. But yeah, it happens real life too. So destructive interference, you saw a little bit there already. What happens? The two waves move towards each other. When they actually meet, briefly we get no sound at all. You might say, wait a second, is this how noise-canceling headphones work? The answer is you betcha. How does it work? There's a small microphone on the outside of your noise-canceling earphones. They pick up the waveform of the sound coming in, and it actually produces an exact opposite wave electronically that gets played in your earphone speaker to exactly cancel out the outside noise. It's not perfect, but pretty doggone good. The idea is this sound, again, they pass through each other and changed, but the amplitude's smaller than at least one of the original waves. You end up with some subtraction going on. What happens if the two waves don't have exactly the same amplitude? Well, then you don't get an absolute 0 point like we did here. But in this case, the amplitude of these two is exactly the same, so it cancels out. If one of these was larger, it wouldn't completely cancel out. We'd end up with the larger one still having a net piece there when they added. What does it look like? Again, this way, here you can see the transverse waves. Here, a crest lines up with the trough. And so when you end up with here is basically nothing. They cancel each other out. In this case, a compression here lines up with a rarefaction here. What do you end up with? Basically nothing over here. No compressions or rarefactions. This is basically what your noise-canceling headphones do. Here's a brain break real quick. In these, I should explain real quick, what you're doing is adding two letters and rearranging these to form a word. These are not easy. This one tends to break people, but if you want to try it real quick, this one's a tough one. So for example, BN or BJN becomes banjo. Notice you have to actually rearrange the letters at times. Pause if you'd like to try this one, or at least try one of these. If you get all 10, you're in the genius category. All right, pause now. All right, here are the answers for each one of these. UUV is uvula, the thing hanging down the back of your throat. JRR is either perjury or jury reg. Unique. Bivouac, that's where armies encamp. Like I said, quartz. Cantata or rat-tat-tat, which are both real words. Flummox, which is a strange word. Unknown, hopefully you maybe got that one. Fjord, Norwegian word that's been borrowed into English. And rainbow. Yeah, they're tough ones. All right. This one I can't do for you, but I will tell you, if you're watching this video, New York Times used to post the bad seat list. A bad seat at a theater? The answer is yeah. In New York City, if you went to a musical, there would be certain seats that were in very, very bad. What was going on? In those particular seats, something interesting happened. This is back before modern acoustics. If you were sitting in that seat, for example, here in the balcony, not only did the sound come directly from the singer to your seat, but it may have bounced off. For example, they love to use smooth ceilings. What might happen? Well, the sound wave that bounced off the ceiling up here would actually travel a longer distance. And by the time it arrived at your seat over here, what might happen? They could be out of phase, where the crest from this wave that was coming straight from the singer met up with the trough from the reflection. And you literally could not hear much of the audio in those bad seats. And so you would avoid those if at all possible. In the speaker demo, you'll discover that if you have two sources of sound at the same frequency, there are places, and these circles represent the crests moving out from each one of these. You'll see that there are places where you get constructive interference, where crest meets crest. This is where you get super loud sound. And normally in a stereo speaker, you set it up so you get maximum sound right along the midpoint, right along here, because usually people set up their couches in their entertainment centers or their seats right along the middle. But there's also constructive interference here and here. The harder one to see is there is also destructive interference. This is where the crest of one wave right here meets up right between two crests of the other one, the dark blue ones. This point, this crest is meeting the trough of the other one. Here's another point of destructive interference, another point, another point, another point. And it turns out there are lines of destructive interference along these lines. That if you're sitting there, you'll actually end up with points where you won't hear anything. This becomes problematic. You need to make sure that if you're sitting here in the middle of your stereo system, you've got the speakers set up so they're producing crests at the same time. That's why speakers have red and black wires, to make sure you have the polarity set right, so they move in and out the right way. Here's actual simulation, computer simulation over here. Here's a ripple tank. This is literally a tank of water, and there's two little things bobbing up and down at this point. And right along these lines here, you can see the destructive interference. You don't see any waves along these lines at all. That's where the waves from the two are canceling. In between these, you get constructive interference, where you've got strong, bright troughs, and the dark lines here are actually crests. So now what happens when a wave runs into something else? And this is where we get some interesting effects. Whoops, sorry, jumped ahead too far. At a fixed or more dense boundary, where in this case there's a pulse here and it's about to run into this material here, this material is more dense. So we say this is a fixed boundary. Waves are inverted when they reflect. The reflected pulse is the same magnitude of the amplitude, but is flipped over. So when a wave hits here, it comes back on the other side with the same amplitude. So you get some interesting effects. So if the amplitude here is A, the amplitude on the reflected wave is A, but it's negative A, if you want to think about it that way. Exactly the same amplitude, but in the negative direction. You can sort of see the animation here, and I'll just talk about it. So in this case, instead of just a fixed boundary actually put, here's our boundary point, you've got a thicker spring over here. And notice what happens. The reflected wave here does come back on the other side, but it may actually come back at slightly smaller amplitude if the other side is not fixed. The transmitted wave actually goes through in the same side. And you can see this in a couple of these animations. The speed, wavelength, and amplitude of the transmitted pulse are all smaller than in the incident pulse. It turns out when you get to a more dense medium, the velocity decreases. So out here, you might have a very large velocity, both there and back, but the wave that transfers in the denser medium is always smaller. Waves travel slower usually in more dense strings. We'll talk about that. Here's a quick example in the hallway. In this case, you'll see a pulse traveling down there, and the person over here is actually a little bit more dense, and you'll see that the wave, when it comes back on the opposite side after it hits that boundary. All right, moving on. A free end reflection. So say, for example, you had this string attached to a ring that was free to move up and down on this one. What happens then? It actually comes back on the same side. So at a free or less dense boundary, waves are reflected on the same side of equilibrium as the incident pulse. So here the amplitude is here, and when it bounces back, the amplitude's also on that side. Might be smaller if some of the energy gets transferred to the object. So take a quick look at this one. In this case, notice that it comes in with some velocity, and the velocity that it comes back with is also the same, but in this case the amplitude gets smaller. Why? Part of the energy got transferred to this less dense medium where it moves at a much larger velocity. This one's harder to do in the hallway, so I didn't make a video. We can try it live in class, but I just want to talk it through. Yeah, the transmitted pulse, larger amplitude typically, and much larger velocities. Last piece I want to talk about is standing waves. If you get exactly the right frequency, you can actually set up a standing wave, and I'll show you what I mean by that. What's a standing wave? Well, you've got certain points which barely move. These points on this animation down here are barely moving. Those are called nodes. But there's also other points on this standing wave where you get maximum changes in position. These are called antinodes, where you get maximum changes. And in a standing wave, you actually get both of these, some nodes and some antinodes. Why are these happening? When the wave runs into a boundary, it gets inverted, sent back, and if you keep sending waves down it, you can actually set up these standing waves. So here's what it looks like. Normally you have a vibrator. In this case, we've got, a little vibration source over here. And you can see the standing wave forming here. Here's nodes along it. My apologies for this fairly bad, quick animation. They are evenly spaced. There's just a little bit of perspective on this one. And then in between here, we've got antinodes. In this case, there are 4 antinodes and a total of 5 nodes. Here's that animation again, this time with a little bit of really super slow-mo. You can actually see the waves oscillating down and up and down this thing, and then back to normal speed just here at the end again real quick. Sorry, I took it during lunchtime, but the room was kind of full. And there it is, back to normal. And then here's a wave machine. Just real quick, I want to sort of show you this one. In this case, you can demonstrate the waves. In this case, I can either connect it with a ring stand here with a clip to make it a fixed end, and watch what happens when you send a wave down this one. It'll actually kind of bounce off. My apology for the blurriness of the background. Wave going in, bounces back on the other side. And you can even set, there's one on the negative side, comes back on the positive side. And you can, now this time I'm going to take that off on the back side so it's no longer clamped. Now this end over here is going to act like a free end or less, where it runs into a less dense boundary. What's going to happen now? You should actually see the fact that we get some interesting effects. Watch what happens. Send in a positive, it comes back on the positive side. Not as large, but still there. And if I send a negative pulse, it comes back on the negative side. So a little bit of mathematics of the standing wave. This happens all the time with guitar strings or piano strings. Imagine the string is normally right along this line here. When you disturb it, it normally oscillates back and forth this way. And that's the fundamental or first harmonic. But it can also oscillate in other ways. If you've got a node in the middle, you can actually have this, which is called the second harmonic. Or even this one where you've got 2 nodes in the middle. Total, I guess I should actually say there's actually 3 in total on this one. 4 total on this one. Here there'd be 5 nodes, 4 antinodes. But you can actually make the guitar string oscillate this way. One of my favorite things classical guitarists will do is they'll pluck a guitar string, and without holding any fret, they'll make it go to the third harmonic or second overtone. How do they do it? They pluck it and briefly rest one of their fingers on the string 1/3 of its length as they pluck it. They quickly remove it, but it forces it to have a note at that position, so it can't oscillate this way. Instead, it'll oscillate at 3 times the normal, or 1/3 of the normal wavelength, or 3 times the normal frequency, or double or 2 octaves up of its normal note, which is really fun. Here's an animation of that, what we're talking about. Again, you can see the nodes at each end of these. And then this one has 3 nodes and 2 antinodes. And this one has, never mind, you get the idea. And so you can sort of see it. And yeah, guitar strings naturally do this, piano strings, any stringed instrument, violins will do these. Mathematically, you can actually do some calculations on this one. Remember, one complete wave looks like this. So how much of a complete wave do we have at any instant? Well, if you look at this, if I do a freeze frame real quick, it's only half of a complete wave. So this length right here, if I call this L, is just equal to half of a wavelength, 1/2 lambda. So what's the lambda, or what's the wavelength of this wave? Well, it would be double the length of this string. Down here, this is exactly 1 wave, 1 complete oscillation. So in this case, lambda is equal to the wavelength, or you can say wavelength is equal to the length. Down here, this is 3/4 of a wave, 1 complete wave plus another half. So the total distance here is 1.5 wavelengths, or 3/2 of a wavelength. So what's a wavelength equal to? It's equal to that. Is there a general equation then? The answer is yeah. General equation for the wavelength. Wavelength is equal to 2 over n times L, where n can be 1, in which case that becomes 2. Or if you plug in 2, it becomes 1. Or if you plug in 3, it becomes 2/3. Yeah, you can sort of see the pattern. And you can continue this on for the fourth harmonic, the fifth harmonic, the sixth harmonic, where n here represents the harmonic number. So real quick on this one, draw a diagram of a standing wave on each line and calculate the wavelength for each system. Pause the video at this time before I show it if you want to give it a try. All right. Doing it, this case, this one would be a standing wave. I'm only going to draw half of it. This would be it. How much of a complete wave is this? Well, this is 1/2 of a complete wave. And we're told that this whole thing is 4 meters long. So what's the wavelength of this particular one? Multiplying both sides by 2, you would get 8 meters. For the second one, you should end up, and I'm going to give myself a guideline here. Coming down. Sorry, hand drawing this one's actually not as fun. In this case, that is a complete wave. In this case, the wavelength would just be the length of the string, which is 4 meters. And then finally, the last one, again, just a couple guide points for myself. Up, down, back around, back around. In this case, this is 3/2 or 1.5 wavelengths is equal to the 4 meters. And so in this case, what's the wavelength? Well, multiplying both sides by 2 and then dividing by 3, I'll leave it as a fraction, 8/3 of a meter. All right. Beat frequency. We've been talking about interference, but you can actually get some very interesting effects if the two frequencies, I'll call one F1 and the other one F2, are not exactly the same. What do you get at this point? Well, you get occasions where, and sort of watch what's happening right along this line, you'll get occasions where the crest will meet a crest, in which case you get constructive interference. Other times, though, you get crest meeting trough, and you get destructive interference. And this repeats over and over again. And what you end up with is this sort of interesting where the amplitude keeps changing up and down. And you may have heard it, for example, if you've been on a multiple engine plane. When they're first starting up, if the engines aren't spinning exactly the same rate, different frequencies, you'll hear this sound as the two engines get into and out of sync with each other. Orchestras do this as well. They'll all play, for example, middle A, and if everybody's tuned, no problem, but if somebody's off key just a little bit, say 1 hertz, you'll hear this they'll beat with the other ones. And so you can listen for that to see if everybody's in tune with each other. Lastly, I want to get into this one. Organ pipes and woodwind instruments tend to do this. So we've been doing standing waves on strings. I want to show you some other ones as well. We know that when waves hit a fixed or more dense boundary, they invert. They come back on the opposite sides. And remember, for strings, that meant we always had a node there. But in this case, something interesting happens. Organ pipes are usually open at one end. Ignore the little baffle, this little triangular piece in here. But what happens in this case, this is an open boundary or a less dense boundary than the metal over here. And so you actually end up with an antinode at that end. And so you can set up standing waves that look like this inside of the organ pipe. Now, most organ pipes are open at the top and have an opening here. But these, you can have these, and you can have these very interesting effects. And yeah, you can calculate the wavelength again. And this gets a little tricky. I just want to mention, how much of a complete wave do we have here? Well, if you look at it, inside this tube, we only go from a node to an antinode right here. How much of a complete wave is this? In this case, this distance right here is 1/4 of the entire wavelength. And so you can actually do some calculations. You can see it over here. Yeah, the wavelength would be 4 times the length of this tube if the length is L. And you can do some fun calculations. We're not going to ask you to do this, but yeah, this is considered the fundamental n equals 1. The second don't worry about it too much, but mathematically you end up with this. The calculation is a little bit uglier than normal. You can also have organ pipes, and these are the more normal ones. And again, normally these things are vertical. If you've ever seen a pipe organ, next time you get a chance, take a look at them. They have openings both here in the bottom and at the top, and usually they're open at the top, and then down below they have a pipe driving them. But in this case, you end up with antinodes at both ends. And so how much of a complete wave is this one? Well, if you look at it, and this is a little bit confusing, that's half of a wavelength from here to here. And so you can actually do some quick calculations to figure out, in this case, the wavelength must be equal to 2L. And you can get first, second harmonic, and third harmonic on this one. And yeah, there's a formula to calculate that as well. Don't worry about the equation. Last thing I want to talk about, and it's just sort of a tie-in to this chapter with constructive and destructive interference, is resonance. Every single thing you've ever seen has a resonant frequency. And what happens when you reach the resonant frequency? The object begins to resonate or oscillate more and more because you're doing constructive interference with the waves that are already inside of it. One of my classic jazz singers is Ella Fitzgerald. Ella Fitzgerald, when she was alive, used to take a wine glass, just grab a random one from the bartender before a performance, and would ting it with her finger. The sound that it would produce would not be a perfect note. It wouldn't be a quarter pitch. It would be just some random one. And then she would go for an entire 2-hour jazz routine. And the last note she would hit in her performance would be the exact frequency of that wine glass, which she had left in front of one of her loudspeakers. And I just want to show you this because what would happen? The glass would resonate. Its amplitude would get so large it would shatter. So here's Ella Fitzgerald. I hope you can hear her.
She's attempting to shatter a glass with her amplified voice. She did it. You are now hearing the Memorex cassette tape recording we just made of Ella. Now you'll see a glass shatter again. But is it Ella or is it Memorex?
So notice the different frequency.
I'll never tell.
She would actually have to do this commercial. They had to find some wine glasses for the recording, but have exactly the same pitch as the one she broke live. Makes it a little bit more challenging. I also want to show you, though, this happens in real life, too. Actually, turn down the sound on this one. This is the Tacoma Narrows Bridge, and some of you may have seen this one already. This bridge is interesting. As wind blew across it this way, this is a particular day, the wind was moving at a constant about 30 miles per hour. And if you've ever blown across a blade of grass or a sheet of paper, you know you can actually produce a tone. In this case, the tone produced, and I won't say it's exactly a tone, was exactly equal to the resonant frequency of the bridge. And so what you end up here is a very interesting situation where the bridge actually resonated with the pitch that was produced by the wind blowing across it. And in just a moment here, that's his car. This is concrete and steel, not designed to flex this much. In a moment here, it's about to catastrophically fail. It's hard to imagine that steel and concrete could actually stay together while flexing like this. But you're going to see what happens in just a moment here. Sorry, my apologies. This is a little bit longer clip than I was expecting. But here it goes. This, by the way, if you're curious, back in the 1939, 40-ish, somewhere in that range. I got to look at the exact date. But nowadays, after this disaster, no civil construction is done without first discovering what the resonant frequency is. In California, that becomes extraordinarily important for buildings. Why? You're like, Ms. Clemmer, is it wind? Yeah, actually, for skyscrapers, wind might cause them to resonate. But more importantly, here in California, earthquakes. Earthquake waves are naturally in the 3 to 10 hertz range. What happens if your building naturally resonates somewhere in that range? Your building is going to undergo a catastrophic failure just like this bridge did. Finally, here are all the equations for the chapter. We've got Hooke's law up here. We've got the equation for a mass spring oscillator here, for a pendulum here, the wave equation, the one we just used here, with a reminder again that frequency and period are reciprocals, the energy of an oscillator, remember, related to the amplitude squared, and then over here I just put the energy formulas just for your benefit. The two equations I forgot to list on this one are springs in series and parallel. We'll make sure we give those to you on your test. All right, good luck with your homework tonight.